Hi, I'm Mark Rendle, and I'm here at the start of the API track to talk a little bit about the history and how we've got to where we are today and where we might be going next, and show you a little bit of code along the way, and generally just get everyone set up for the day. Who's planning on spending most of the day in this track? Quite a few people, so yes. There should be some interesting stuff. I'm expecting lots of different people to come along and say, this is the right way to build an API. And then at the end of the day, you'll have 8 right ways to build an API, and you can just go away and choose which one you liked the best. So, brief history. I will try and explain how we got to where we are. From the 1970s, which is when really programming kind of got started. People were doing stuff with COBOL and Fortran, and we were just starting to get into high-level languages like C and everything else. And so we had to create application programming interfaces. We had to create ways that if we made a piece of software, whether that was an order management, stock control, usually finance back in those days, banks were early adopters, and they had lots of different applications dealing with different things, and those applications needed to be able to talk to each other. And so they had to create APIs. And we've been using APIs as programmers. Pretty much everything we use could be considered an API. Even the programming languages that we write code in, whether that's C or C# or Java or Python, there's a piece of software which might be a compiler, or it might be a dynamic language runtime. And we are using the API for that compiler or dynamic language runtime to use that to create our software. And then everything we interact with, whether that's a database or a messaging system or a queue, that has an API that we talk to as well. And then, of course, we've got the higher level APIs now of talking to other sort of services in service-oriented architecture or microservices. But back in the 1970s, things were largely running on mainframes, and that very few people, very few organizations in those days would have had more than one mainframe. That kind of wasn't the point of mainframes. You bought a mainframe, and if you needed more processing power, you bought a bigger mainframe. Or you made your mainframe bigger because you could just buy another couple of fridges and tack it onto the end and add another 2 megabytes of disk space. Just a little bit about me. This is actually my 31st year as a professional software developer. I've been doing this since I was 16. I started on Unix systems with Wise terminals. My first day at work, they said, learn C, and they gave me the Kernighan and Ritchie book with Hello World and a Wise terminal, and I sat down and I said, how do you edit files? And they said, use VI. And then I spent 6 months learning VI. But the mainframes that existed, they had lots of they had time-sharing systems, they had multiple processes running, and those processes needed a way to talk to each other. And so one of the first examples of an inter-process API was message-oriented middleware, or MOM, which was pioneered by IBM in the 1970s. Anything that was pioneered in the 1970s, you can pretty much assume it was IBM pioneering it. And message-oriented middleware was what we would think of now as RabbitMQ, really, but with a little bit of intelligence so that something could send a message and then that middleware could transform it and then send it on somewhere else, and that might get a response back, but it was very asynchronous, and it's the sort of thing that we do today, and we think we're being very clever using Kafka or RabbitMQ or AMQP, and we're basically doing the same thing that people on mainframes were doing with COBOL and MOM in the 1970s. The other API that was created then, it was ISAM, which is how databases used to work. The first database I worked on was Infomix SQL. Any Infomix people in the room? No, just me. Yes, one at the back there. Other people were doing Oracle. Somehow I ended up at a place that was doing Infomix. Infomix was obviously superior. But an Infomix SQL database was just a bunch of CISAM files, and we used a library called CISAM to talk to the ISAM files. And then Infomix invented ESQL-C, where you would put dollar symbols into your C code and write SQL statements in it. And then it would go through a pre-compiler that just turned those into the CISAM API calls, and then it would compile and link. And we had a table tennis table, because compiling and linking in those days used to take 3 hours. And if you broke the build, you had to stay and fix it for the next morning. And if nobody broke the build, then whoever lost the table tennis tournament had to stay and make sure everything was ready for the next morning. Then the 1980s happened, and object-oriented programming came along. And object-oriented programming made APIs much easier to build, because you could create an object and you could send it off to somewhere else, and then you would get another object back telling you what the result was. And that might all have been in a single process. Alan Kay, the creator of Smalltalk and object-oriented programming generally, wishes he'd called it message-oriented programming, because he says people got completely the wrong end of the stick. They thought object-oriented, and they started talking about dog being a subclass of animal, and animal being a subclass of mammal, and whatever else was going on. It was message-oriented programming. And so within the process, within the libraries and the frameworks that you're using, you have an API. I use .NET, and when I want to talk to the file system, I use things in the system.io namespace to talk to the file system, and that's an API. We also got shared libraries in the 1980s. On Windows, we had DLLs, so you could publish your software with a DLL, and then somebody else could link to that DLL using a .h file, and then they could consume functions that you distributed, which made it easier to access your file formats on the file system. Did anyone use mappy.dll back in the day to interact with their mail system? You have my sympathy. We also had OCX, which was kind of the early ActiveX things, and on Linux we had shared objects. And Microsoft, of course, invented dynamic data exchange, which was a way of talking between two processes running on the same machine. I have very unhappy memories of working with Excel over dynamic data exchange from VB6. And we also got sockets. That was a 1980s thing. Network sockets, but also Unix sockets, domain sockets, nice ways for two processes to talk to each other on a system. In the 1990s, client-server came along, and everybody went rushing for clients. And client-server basically meant you have a Novell NetWare box, which is running your database, or a Unix box, or a Linux box. And then you have rich client applications on lots of Windows 3.1 machines or Windows 95 machines, and they talk to the database over the network. And that database protocol was an example of an API, and SQL is a good example of an API language. We also got the Common Object Request Broker Architecture, CORBA. Are there any CORBA casualties in the room? How's the PTSD? Yeah. It's still out there. People are still using it. People are still getting stuff done with it. And good luck to them. Microsoft decided that CORBA, IBM basically had control of CORBA, as they did with a lot of the standards. And Microsoft went, we're not doing CORBA. We're going to do the component object model. We're going to do COM, ActiveX. And if we want to do messaging over the network, we'll do DCOM and COM+. And it was Microsoft's answer to CORBA, which basically became widespread simply because everybody was on Windows at that point. COM, incredibly good fun writing COM code in C++. That is not something I would recommend doing. And of course, in the 90s, in 1993, Tim Berners-Lee invented the World Wide Web. British, yes. Back when we were something. Although, of course, he invented it in Europe. I'm not going there. But the World Wide Web, that's just a massive API. That's just a way of talking to other machines and saying, give me back some HTML and some images and everything else. And so this was the point at which the API really became the default. It was the default way of interacting with computers. You would create some software. That software would talk to a variety of APIs in order to do its job. And so on top of that, we invented service-oriented architecture. We said, it's ridiculous that all these client-server systems, bear in mind we're still in the same decade where we thought client-server was a great idea, but by the end of that decade, we're going, client-server is a terrible idea. We've got all our business logic, and we're repeating it over and over again on all these desktop machines. We should be pulling that business logic out of there and putting it into services that we're running over HTTP, and we should be talking to those from the clients. And so we started to move towards this idea of a thin, smart client that could talk to these back-end services. And just to make sure that all these back-end services could talk to each other and all the different clients could talk to those back-end services, we had to come up with a common language that they could all speak, and so we invented SOAP. Sorry. If you're too young to remember SOAP, if you haven't been doing this long enough to remember SOAP, then yeah. In the year 2000, Roy Fielding at the University of California, Irvine, for his doctoral thesis, wrote a paper called The Architectural Styles and Design of Network-Based Software Architectures, which you may know better as REST, or Representational State Transfer. It's one of those occasions when somebody's doctoral thesis has become a rallying point for zealots to start bashing everybody else over the head and generally being unpleasant. The other one obviously being Karl Marx's Das Kapital and the Soviet Union. Yes, I did just compare REST zealots to Stalin. Because I can. Also in the year 2000, or in the 2000s, we got XML HTTP request in browsers. XML HTTP request was actually invented by Microsoft, and it was built into the Internet Explorer browser, and they only invented it. They never meant for it to be this whole AJAX thing. They never meant for Web 2.0 and everything else to happen. They literally invented it to make Outlook web access work, so that every time it checked for mail, it didn't have to refresh the entire screen and re-download all those ActiveX controls. JSON was created in 2001. Douglas Crockford created JSON as a subset of JavaScript. So the idea was that if you you created a JSON string and then you passed it across the network, you could literally just exec it, because dynamic languages, on the client side, and it would become an object, and then you would be able to work with that object in your JavaScript code. Which, of course, is a terrible idea, because all you have to do is put something nasty into the JSON, and the JavaScript client will exec it. And so we ended up having to get JSON.parse anyway, which completely negates the point of JSON being a subset of JavaScript, but never mind, it still is. In 2006, service-oriented architecture was just about to run out of steam, really, and so Microsoft invented Windows Communication Foundation as a way of doing service-oriented architectures, and I'm sure most of the people who raised their hand for whodoes.net will have done WCF in the past. We'll be looking at that in a bit more detail later on. REST came out of Roy Fielding's very vague thesis, and also in 2006, I think it was, Apple introduced the iPhone. Microsoft had been trying to make smartphones for about 3 or 4 years, and Apple just kept their powder dry, waited until capacitive touchscreens came along, and then went, here you go, that's how you do it. And who hasn't got a smartphone in their pocket? See, that's a good one, because you don't have to raise your hand. But mobile devices obviously made a big difference. We suddenly got to this situation where you wanted the data on your mobile device to be current, and so we created systems that would talk to APIs pretty much exclusively. We couldn't run databases locally on that machine. We couldn't do the thing that we'd been doing with sort of salespeople going out with laptops with a local copy of the database, and then they'd come back at the end of the day, and we'd run a SQL Server merge replication synchronization and wonder why all our tables had disappeared. And the late 2000s was also when we started to get what we actually think of when we say APIs now, which is public APIs over the internet to services and software that's hosted on the internet. So eBay introduced their API actually in the year 2000. I'm quite surprised that eBay is 20 years old, but it is. And so the eBay API, they invented so that people could write bots to snipe auctions. I think that's the only reason they did that. Amazon created their first API in 2002 so that people could search the Amazon stock database and display information from Amazon's store on their websites. Twitter came along with their API in 2006, and I think Twitter's one of the best examples of a company launching with a very, very good API and giving everybody access to that API and saying, build stuff based on this. And there was a plethora of amazing Twitter clients that people built. And whatever you wanted to use Twitter for, whatever Twitter meant to you, you could find a client that consumed that public Twitter API and represented the data in a form that was meaningful to you. And then 3 years later, they shut it down and said you couldn't do that anymore. And Facebook in 2007 introduced the Facebook platform so that you could automate giving your personal data to Twitter, and you didn't have to sit down and do it with a mouse and a smartphone and a camera. And the other thing that we started to see in the 2000s was a very busy decade. And then last decade was even busier, and this next decade I'm seriously considering just staying in bed and seeing where we end up in 2030. But we got cloud computing, and Amazon suddenly realized, Jeff Bezos in Amazon had internally told all the teams building all the different bits of Amazon, everything should be an API. So every team should be able to consume everything from every other team using an API that you have published documentation and specifications and libraries for, regardless of what platform they're using. So we've got some people who are doing JavaScript, we've got some people who are doing Python, we've got some people who are doing C++. All these things should be able to talk to each other. And he extended that even to the provisioning of infrastructure, virtual machines and storage and everything else. And then at some point went, hang on, we've got this amazing object storage platform and we've got lots of spare capacity on it. Why don't we just sell access to that? And so they created S3 in 2006. And so if you had something that was running on the internet and you needed to be able to store data somewhere, you could just say to Amazon over their API, hey, can you store this for me? And it would keep it, and you would pay based on the amount you had stored as well. And this is another trend that was introduced at around this time with APIs, was the pay-as-you-go model. So rather than buying a license to a piece of software, buying like SQL Server and then having to pay per core that you're running it on and provision a piece of hardware for it, you had an API and you could say create a bucket in this data center here, and for every gigabyte of data that I store in there, I will pay 3 cents per month. And the API became a unit of sales as well as a programming tool. Microsoft, this is not clicking. Microsoft introduced Azure in 2008, and it was actually called Windows Azure back in the day, before Satya took over and decided to deprecate the term Windows. And that had a similar set of things. And then since then, we've seen other people come along, obviously Google, IBM, but also smaller companies like DigitalOcean and Rackspace have managed to compete with the big players by providing APIs to their services as well. And then we got into the 2010s, and I can't remember exactly when it was everyone started talking about microservices. It feels like 30 years ago, but it's not. It's much less than that. But microservices is taking that idea of service-oriented architecture to its extreme. I listened to a blog, not a blog post, I listened to a podcast a while back with a microservices person who was suggesting that every single object in a framework had the potential to be a microservice. And they said, what, int? And he said, yes, why not? Yes, I'm provisioning an integer in US East 1. And the funny thing was, when people started talking about microservices, I was doing .NET development. I was creating ASP.NET Web APIs. At the time, that was the kind of an ASP.NET MVC websites and WPF applications that talk to those ASP.NET Web APIs. And everything had to be hosted on IIS, on a Windows server. And provisioning Windows servers with IIS was not fun. And deploying an ASP.NET website onto IIS, considering they call it the integrated pipeline, deploying an ASP.NET website onto IIS is way more complicated than it should be. And so the idea that we were going to create even more smaller web APIs and deploy them all over and over again, sort of 2 or 3 times a day, was absolutely insane. I couldn't see that at all. Microservices didn't really make sense until containers came along. Docker put a layer over C groups and everything else, and Docker created an API, an approachable API, over the namespaces and C groups and boundaries and process limits and everything else that are inside Linux, and they called it containers, and they gave us a command line interface to interact with it, and they gave us an HTTP API to interact with it. You could connect to docker.sock, and you could send HTTP requests, or you could connect to your Docker server in the cloud, which of course you'd secured with an SSL certificate. And you could spin up machines and scale and do everything else. But even that was a bit too complicated for most of us. And so then we got Kubernetes. And Kubernetes is the ultimate infrastructure API. And it's evolving and evolving. And we're getting to the point now where Kubernetes actually has APIs built into it, where you can say to a Kubernetes cluster, provision another Kubernetes cluster inside this cluster. I want to create virtual mini clusters inside my cluster and do interesting things with that. But once we got containers and Kubernetes, it became very, very easy to deploy services over and over again. It really enabled that continuous integration, continuous delivery pipeline. And we leveraged APIs all the way through. So we had webhooks, and you would commit something into GitHub, and that would trigger a webhook, which would fire off your continuous integration on Jenkins or Bamboo or Azure DevOps or whatever you're using. And then that would build your software, and it would run the automated tests, and it would potentially create Docker images and push those to a registry. And then pushing that to a registry would trigger another webhook, which would call another API, which would then deploy that new image into production and slowly cycle down the old one. All done with APIs, and mostly over HTTP still at the time. And we also got WebSockets. And WebSockets was a way of browser. At this point, we'd started building everything into the browser. Everything was just a browser application. And so a WebSocket was effectively TCPIP, but in the browser, you could open a persistent connection to a server and just send data backwards and forwards over it. And we could build the same kind of experiences inside the browser that we'd been able to build with things like WCF or whatever it is you Java people use, I don't know, Spring or something, isn't it? Seriously, I have no idea. But I love you. You're great. So one thing that all these APIs have in common is they need a way to talk to each other. The client needs a way to express a request, and the server needs to be able to understand that request and act on it, and then create a response, and then the client has to be able to understand that response. And there are two real things involved in that process. One is, how do they send that backwards and forwards? Is it over TCP or HTTP or through a shared file system or some shared memory? And the other is, what format are we going to use for that message that we're passing between the client and the server that they can both understand? And this has gone through a very interesting evolution. I researched it for this talk, and it's quite fun. One of the earliest sort of wire format standards was CORBA, and what was called the GIOP, or General Inter-Orb Protocol, because CORBA was all about the orbs, apparently. And this was a binary format, and it was very efficient. And it had to be, because when we were using CORBA to build our distributed systems, we were still dealing with 10 megabit Ethernet networks. In some places, we were still dealing with the token ring networks, where if somebody removed the terminator from the end of the network, then the whole thing would just stop, because the messages would just go flying off the end of the network and into space. But that lack of network bandwidth and the absolutely appalling amount of error correction that was needed, because the network wires were very shoddy and people like me were soldering them, and I'm not good at soldering. And so we had to keep the messages small. And so CORBA used a binary format. It was very complicated, and ideally you used a library to create it, but you can see the general outline of a CORBA message or a GIOP message. And then this was sent over IIOP, which was a TCPIP-based protocol for two orbs to talk to each other in a distributed CORBA system. Now, obviously, debugging this was quite difficult. If you used Wireshark to attach to the network and look at the messages that were being sent, you'd go, I have no idea. I don't know what that is at all. And so we decided that it was very important that we should be able to read the messages being sent between these machines, as well as the machines being able to read the messages. And network bandwidth went up a bit. We got to 100 megabit networks. And so we grew complacent and said, yes, we can just use text to talk between systems. And so we invented XML. One thing I will say about XML, this is a current piece of XML that I invented from a current system that doesn't really exist, but it's still version 1.0. How many things after nearly 25 years are still 1.0? They did a really good job with XML when they spec'd it out, and XML was the first kind of common human readable format for a given value of human. And we could use XML to communicate between systems, and everything was fine and great. Interestingly, for me, the XML 1.0 specification came out on the 10th of February 1998, which was my 25th birthday. So now when my kids ask me how old I am, I say I'm 25 years older than XML. And they say, God, Dad, you're such a geek. But of course, XML, it's almost perfect. It's wonderful. As long as you've got the network bandwidth, it's easy to read for a human. It's easy for a computer to parse, kind of. And it was just generally quite nice and easy. So of course, we had to improve on it, and that was how we got SOAP. And this is SOAP. So SOAP essentially wraps the XML with a bunch of things that say SOAP. And it also adds namespaces into the mix because the XML people were very clever and they went, what if two people have two different schemas, have two different sort of XML objects, and they both have a description field? We need namespaces so that they can say this object has this description field and this is this namespace. And so that was the other thing that SOAP made compulsory as part of your XML, was an absolute shed load of namespaces. And I think part of the reason I dislike SOAP so much is because working with namespaces using the XML libraries in .NET is not fun. It just isn't. And the other thing, of course, with XML is that there were a few special characters, the greater than and less than symbol, the apostrophe, the quote, and so we had to have, where are we? We had ampersand apos semicolon. So what was a single byte character became 5 bytes over the wire. Then JSON came along, and JSON, like I said earlier, Douglas Crockford, the idea was that it is just a JavaScript object, and JSON's great for moving data across, and particularly for moving data between web servers and browsers. Browsers can understand it easily, they can process it easily, and so we decided, never mind XML, we're going to use JSON for everything. We're going to use JSON for our configuration files. JSON doesn't support comments. Never mind. Why would we have comments in our configuration files? That's just insane. And of course, the other fun thing with JSON, dates. No standard way of representing a date in a JSON object. So Douglas Crockford, he kind of came up with the idea in 2001. The JSON.org website went online in 2002, and it just took 11 short years for it to become an actual ECMA standard. So there were, from 2002 to 2013, if you downloaded a JSON package for your preferred development system, it was kind of 50-50 whether it was going to work with the JSON coming from the other system that you were talking to. Now, we have something called Protobuf. And Protobuf is Google's format for messages, and Google created this in 2001. Google were effectively one of the first organizations to build a massive distributed system. The Google engine itself, the search engine, was a massive distributed system. Obviously, the MapReduce algorithm, you had a bunch of servers doing something and then aggregating those results and sending it to a smaller set of servers and then another smaller set of services and then eventually down to the browser where it became a series of advertisements. And even though we were up to gigabit networking at this point, and even though they had tens of thousands of machines in their data centers, the amount of traffic they were passing in between the services meant that they had to make it as small as possible. And so this is not actually Protobuf. This is how you define a message in Protobuf. This is how you would define the book message from that XML. Once you've run the Protobuf compiler and it generates the stub classes for you and then it produces the actual wire format, Protobuf looks like this. That is a hexadecimal representation of exactly the same data that was in the XML and the SOAP message that I showed you earlier. This is 101 bytes, and the equivalent SOAP message was roughly 600 bytes. And so it's an awful lot smaller. And it means you can send 6 times as much traffic over the same network. The other nice thing about Protobuf, I said XML is easy to parse. It's actually, try writing an XML parser sometime. It's not fun. Protobuf was designed so that encoding and decoding the message is efficient as possible, regardless of the language that you're doing it in. Whether that's Python or C# or Java or C++, whatever it is, it's designed to use a minimal amount of CPU power to actually handle the encoding. There are some other wire formats which are in use at the moment. There's Thrift, which was open sourced by Facebook in 2007. Thrift is a very similar alternative to Protobuf, but is more kind of RPC oriented. There's Avro, which came out of the Hadoop project, which is kind of somewhere between Protobuf and JSON. So Avro messages actually include the schema for decoding that message inside there, whereas both Thrift and Protobuf, you have to have generated a class that understands the message. It's very difficult to reflect over it. We have MessagePack, which I really like. MessagePack is very fast, very small, but it's basically JSON. It's just JSON encoded in a different way. So instead of actually having the field name, you just have a byte, and both the client and the server know what that byte means. It goes, this is the description field, this is the title field, it's a string, it's going to be this long. BERT, I have no idea what BERT is. I just found it while I was doing my research. It's got the best name though. It's actually the binary Erlang term, and it's how Erlang distributed systems speak to each other. And of course, BSON, which is just binary JSON. That's the internal format used by Mongo, but it is a standard, and you can use it to communicate between systems if you want to. And then, as I said, there's two components to this. One is the wire format. How do we encode and decode the data at the client and the server end? And the other is protocols. And when we first started talking between systems on networks, the protocol was TCPIP. It was sockets. And you would just open a socket at your end. You would say, hello, can I have a socket on that machine? And that machine would say, yes, I am now listening on this socket. And you would send data backwards and forwards over that socket connection, and everything else was down to you. And you get a packet at a time, and if the packet didn't contain your entire message, you would have to buffer that packet, and you would have to deal with framing yourself. TCPIP actually started development in 1973, like me, and ARPANET migrated to it on January the 1st, 1983. So we've had TCP since then, or TCPIP. And it still runs the entire internet today, and will do for the next couple of years, and then we're all going to go to HTTP 3 over QUIC, which is UDP, which is unreliable messaging. That's going to be fun. But yes, TCP/IP is raw, and it's fast, and it's painful. And if you can handle the pain, it's the most efficient way to pass data between two systems. Then we got HTTP 1.1. This was Tim Berners-Lee contribution to the world. HTTP, really, really easy to understand. You can actually look at an HTTP request and you can tell what's going on and you can understand it. And it's quite efficient, and it can handle binary data. It can do all sorts of things, and it takes care of that framing problem for you. So the HTTP headers, ideally, if you've written a good API and you have well-behaved clients, will have a content length header. And so you can actually go, right, so from this double new line here, I need to read for this many bytes. Unless somebody has told you how many characters there are in the string, rather than how many bytes the UTF-8 encoding requires. HTTP made it very, very easy for us to build APIs, but we needed a standard way to actually represent those APIs, which was where everybody got completely nuts about REST and Hypermedia. It was just, yes, I can send data over HTTP, but I don't know if you're going to be able to understand it. What would be really nice is if I could send you an HTTP request that I know about, and you could send me back the data along with some information about some more HTTP requests that I could make to do things with that data. And this was kind of API on steroids. If you did REST properly, if you did, I saw this referred to as HATOAS, Hypermedia as the engine of application state, which was kind of level 5 REST or something. GitHub's API has always been very good at this. If you go to GitHub's API and say, give me a repository, give me the data about a repository, it will send you back all the information about that repository, but embedded in there are URLs that said, here is how to get the code, here is how to get a list of the files that are in this repository. And so you could write your client to understand that those URLs were in the text and then use those to do further requests, which meant that GitHub, at their leisure, could just change those URLs anytime they wanted to. And as long as the object had the new URLs in it, then your software would still work. Don't get into versioning, though. That's a nightmare. Versioning, REST. There's a debate on how to version your REST APIs on Google Groups that has been raging since the year 2002. NetTCP, so the WCF people in the room may have used NetTCP in the past. NetTCP was Microsoft's proprietary networking protocol for two .NET systems to talk to each other over a TCPIP connection. It was insanely fast. It's a binary format similar to Protobuf or the CORBA object format. It would maintain a persistent connection. The server could say things to the client without being asked. Very, very powerful, and only worked between .NET systems. And Microsoft actually published the specification for NetTCP, how the protocol worked, how the encoding format worked, and went to the Java people, which at the time was Sun Microsystems, and said, hey, you can make your Java systems talk NetTCP. And the Java people went, yeah, no. But it was binary, and it was very fast, and it only worked with Windows Communication Foundation, and this was Steve Ballmer era Microsoft, so of course it was proprietary and closed source. Meanwhile, at Google, for their internal systems, they were using Protobuf to communicate between those systems. But they created a protocol called Stubby, an RPC framework called Stubby, which was used to actually handle the communication between those things. It was called Stubby because you fed in a Protobuf file and it would generate stubs. And those stubs were either a client or the base classes to implement a server in C++ or Java or Python, which were the three languages in use at the time. And it was completely internal. They built it for themselves, so it never got open sourced. It would not have been fun, but it was binary and it was fast and it was internal to Google. And it was when HTTP2 came along that a lot of the code that had gone into Stubby had actually informed some of the design of Stubby, which was Google's HTTP replacement, which everyone went, oh, Google, Chrome, Google running the internet, it's not good. But actually, no, that is quite good. Yeah, oh, okay, let's adopt that. And so then Stubby became HTTP2, which meant that the internet protocol that everyone was using now had an awful lot of the code that had come out of Stubby to do with multiplexing, passing messages backwards and forwards, maintaining persistent connections. HTTP2 has all that stuff, and so Google rebuilt Stubby on top of HTTP2, and they called it gRPC. And the G does not stand for Google. No, it doesn't. It stands for a different thing with every different version of gRPC that comes out. It stood for glorious, ginormous, grand, general, but definitely not ever Google. And gRPC is binary, and it's fast, and it runs over HTTP2, and it was open sourced by Google in 2015. And so now we can all use that. And I'm going to show you a bit of gRPC in a moment. The other thing that we've got now is GraphQL, and I think somebody's going to be talking about GraphQL today. GraphQL it's like an evolution of HTTP APIs, works particularly well for clients for browser clients talking to servers. One of the issues with a standard RESTful API is you might go to GitHub and say, I just want to know who owns that repo. And GitHub will say, yes, here is all the information about that repo. And you just throw most of it away and go, right, this is Dave's repo, and now I know who to go and hit. GraphQL attempts to address that, and GraphQL was open sourced by Facebook in 2015 and is now the standard way of interacting with the Facebook API. And it works really well for Facebook because if you just want to know someone's relationship status, which, let's face it, is what most people use Facebook for, you can just send a request to Facebook and say, what's that person's relationship status? And it will just send that one word back. And so GraphQL is very good for public APIs, for allowing people to request exactly the shape of the data that they want and to express complicated queries. So you can send a request that says, give me all the people in the staff database whose job title is something to do with HR. GraphQL, I believe the idea with GraphQL is you could tell it to serialize as XML, but everybody does it with JSON. But it's very efficient because you get to specify which fields you want. It's very flexible for the people who are consuming it. And if you are building public APIs and you want to give people that flexibility, then GraphQL is probably the current state of the art. There's also something new called OurSocket, which I've been watching with interest. And OurSocket came out of Netflix, again in 2015. Who does reactive programming? So observable streams or RX or Angular sort of, if you're using Angular, you're doing reactive programming, whether you know it or not, because underneath Angular is all RxJS and everything else. And OurSocket takes that idea of reactive programming and applies it over your network. It's a lower level protocol than gRPC. It's OSI layer 5 or 6, whereas gRPC, because it's over HTTP 2, is OSI level 7. But OurSocket, you create a stream between two machines, and you can send messages either in one direction or both directions over that stream. And when you're dealing with those messages at each end, it's up to you how you deal with those. But you can use a reactive framework, an observable, or something else. So OurSocket uses reactive stream semantics. It's lower level, and there is an OurSocket RPC framework on top of that, which turns it into something like gRPC. So I'm going to very, very quickly talk about the difference between, that's interesting, that animated that. So WCF, I have been building for the last year, in my spare time, a product called Visual Recode, which Microsoft announced at Build last year that they had finished adding new features to .NET Core, which is the new open source cross-platform version of .NET. And that in future, .NET Core was going to be called .NET. And so the next version of .NET Core would be .NET 5. And hundreds, thousands of people in enterprises who had built massive distributed systems using WCF said, but you haven't ported WCF to .NET Core. And Microsoft said, no, we haven't used gRPC. And the world went, we can't use gRPC, everything's in WCF. WCF is very structured. You have interfaces and contract declarations and everything else. And so I did an experiment to see whether I could use Roslyn to read the WCF code and generate the equivalent gRPC code, and it turned out I could. So now that's a Visual Studio extension, and it's going on sale hopefully this week. I've just finished the trial thing. Writing trial modes in software is really annoying. I'm going to cripple my software until you pay for it. Feels very mean. But WCF, the thing with WCF, it will allow interop with other systems written in Java or Python or C or C++, but only if you used SOAP. As I said, the NetTCP encoding was proprietary and only worked between .NET systems. And it meant that you had to write your server in C# or VB.NET. There was not a lot of flexibility in there. You could use WCF to generate a client to talk to another server that was written in Java, as long as it published a WSDL file. You could only run your WCF services and your NetTCP WCF clients on Windows, because this was 2000s Microsoft. And it generated subclasses either from WSDL, or if you're using NetTCP, it would just go in and look at the code. gRPC, which is the modern alternative and the one that Microsoft are recommending, its wire format defaults to Protobuf, but you can customize it. If you want to pass message pack messages over Protobuf, you can do that. Over gRPC, you can do that. Don't, because it's insane, and Protobuf is fine, and why would you want to use anything else? But you can if you want to. gRPC supports C++ and Java and Python. It's completely cross-platform. All of these systems can interop with each other. All of them, you can generate a client, you can generate the base classes for a server using the Protobuf compiler, or for some languages, there are third-party open source compilers. So down the left-hand side is the official supported one. So if you go to the gRPC repository on GitHub, all those languages have official first-party support, and then down the right-hand side, you've got all the third-party people. There's a Rust implementation, a Haskell implementation. There's even a Perl implementation, if you really must. I believe it's just one massive regular expression. And don't ask whether it works in Perl 6. I'm going to very, very quickly show the difference, and I'm going to have to switch to duplicate. And then I'm going to go to here. So here we have some WCF, and I'm going to get rid of that, and I'm going to make this bigger. So this is a WCF contract, and with WCF, the whole idea was that people who knew C# should be able to do everything in C# and never have to learn anything else, which describes C# programmers really well. Or it used to. We've got a lot better. No, really, we have. But you had data contracts, so these defined your messages. You had data contracts there like that, and then you had service contracts, and your service contract was literally a C# interface, and then you would create an implementation of that interface. And if I go to there, you see we've got service contract, an operation contract, and everything else. Everything outside of the WCF code was actually just your business logic, and you would map it up to that. I was told I could do a couple of minutes over soon, because the other guy ran over, so am I. So yes, fundamentally, when you define an API, 90% of the code in that API is going to be your code that actually does stuff, and only 5% of it is going to be the bit that actually either communicates with another API or exposes your service as an API. And if you mix those two things together, then you're doing it wrong, which I think is the big takeaway. WCF made it very easy not to mix those two things together, which made it very easy to write a system that would take that WCF code, not now, and turn it into the equivalent Protobuf code. So that is literally the exact Protobuf representation of the service contract that you saw previously. And I have successfully managed to write a system that takes a WCF API and turns it into a gRPC API. And having done that, I'm moving on to taking a WCF API and turning it into a JSON API with Swagger and everything else. And I'm doing a panel later on where I believe we'll be having a brief discussion on this problem of API standards changing over time and how you can migrate from one to the other with minimal disruption to your business. So that did go very long, and I am very sorry. And let's just go back to duplicating, to extending, which should get that onto there. And you can see my lovely desktop. There we go. So yes, I haven't got time for those, but just briefly, so the future of the API, the things that are going to be affecting this in the very near future, we now have 5G networks. Those are starting to roll out across the world. And so mobile devices, we're going to have more connectivity. We're going to have more services being used, more APIs being built and consumed. Satellite internet, Elon Musk is gradually blanking out the night sky with his satellites, which are going to introduce latency issues and everything else. We've got a whole swathe of new devices coming along. I've got a smartwatch on here that's talking to APIs on my phone over Bluetooth. Mixed reality, we're all going to be walking around with augmented reality sunglasses on in 10 years' time. And those are going to be constantly communicating with various servers to overlay advertisements on the real world. We've got voice APIs. When you talk to Alexa or Google Home, you are effectively interacting with an API using your voice. And we've got the Internet of Things, which is lots of tiny little devices with very low power running on batteries the size of a pound coin. And we have those talking over APIs to the cloud. And so that's something we've got to deal with as well. And so, yes, this is where we are. This is where we're going to be going. If you're not building APIs right this moment, you are probably going to be very soon, because it is becoming the standard way. Someone will create a user interface, but the majority of us will be creating APIs for those user interfaces to consume. And that is the end of my brief history of the future of the API. Thank you very much, and I hope you enjoy the rest of your day.